Hey there. Ready for some serious physics?
I think we're ready to spin to some serious physics.
Today's deep dive is all about rotational dynamics, the hidden forces behind twirling dancers, um, rolling wheels, and even the planets orbiting the sun.
Yeah, it's going to be a lot of fun.
You might be surprised how much this stuff uh, affects our everyday lives.
Oh, it's true. Rotational dynamics is everywhere once you start looking for it. And it's not just about things spinning in circles. It gets into how objects um, resist changes in their motion.
And how they react to forces applied at different angles.
Right, and a whole lot more.
Okay, so before we get lost in space, let's start with the basics. What exactly are we talking about when we say rigid body in physics?
Well, imagine the most solid, unbreakable object you can think of. In physics, a rigid body is an idealized system of particles where the distance between each particle remains fixed,
Fixed no matter what.
no matter what forces are acting on it.
So it's like assuming a spinning top is perfectly solid, even though in reality it might bend a tiny bit.
Exactly. Real-world objects are never perfectly rigid, but for most calculations, we can treat them as if they are.
To kind of simplify things.
Yeah, this simplification allows us to focus on the rotational motion itself, without getting bogged down by the complexities of materials bending or flexing.
Makes sense.
Wow.
Now, I'm guessing there are different types of rotational motion, right?
Yeah.
It's not just about spinning around like a top.
You're absolutely right. We can categorize rotational motion in a few ways. There's fixed axis rotation, like a fan blade spinning around a central point.
Yeah.
Then there's rotation about an axis that's also moving,
Okay.
like a rolling ball, which spins and moves forward simultaneously. And things can get even more complex, like a spinning top wobbling as it spins.
Whoa, okay. Let's not get ahead of ourselves. For this deep dive, we'll probably stick to the first two types you mentioned.
Sounds good.
But it's cool to know those crazy wobbling scenarios exist out there.
They're out there.
Now, how do we actually measure all this spinning? I'm guessing meters and seconds aren't going to cut it here.
You're right, we need a different set of tools. Instead of meters, we use angles to measure how much something has rotated. And just like with linear motion, we have angular speed, which tells us how fast something is rotating, and angular acceleration,
Okay.
which tells us how quickly that rotation is speeding up or slowing down.
So it's like the rotational counterparts to speed and acceleration. But instead of moving in a straight line, we're talking about spinning.
That's a great way to think about it.
So it's like the same concept.
And just like with linear motion, understanding these angular concepts helps us predict and analyze how rotating objects behave.
Okay, that's starting to click. Now, one concept I found really intriguing is moment of inertia. It's not just about how heavy something is, right?
No.
It's about how that mass is distributed.
Exactly. Moment of inertia is all about an object's resistance to changes in its rotation. A figure skater spinning with their arms outstretched will speed up when they pull their arms in, even though their mass hasn't changed. That's because they've decreased their moment of inertia by bringing their mass closer to the axis of rotation.
So a hollow sphere and a solid sphere with the same mass will have different moments of inertia, which would affect how they roll down a hill.
Precisely. The distribution of mass plays a crucial role in determining an object's rotational behavior. It's why flywheels, which are used to store energy in rotating systems, are designed with most of their mass concentrated around the rim. This increases their moment of inertia, allowing them to store more energy and spin more smoothly.
Wow, I never thought about flywheels that way. Okay, so we've got these spinning objects, but what actually gets them spinning in the first place?
That's where torque comes in. You can think of it as rotational force, the oomph that causes an object to rotate. When you use a wrench to tighten a bolt, you're applying a force at a distance from the bolt's axis of rotation. The further away you apply that force, the more torque you generate, making it easier to turn the bolt.
So it's not just about how much force you apply, but where you apply it and the angle at which you apply.
Exactly.
Got it.
And the same principle applies to everything from opening doors to the engines that power our cars. Understanding torque is key to designing efficient rotating systems.
So we've got torque making things spin, but what keeps them from spinning out of control? What's the force that balances things out?
That would be rotational equilibrium.
Okay.
It's the state where the sum of all the torques acting on an object is zero, meaning there's no net rotation.
I see.
Think of a perfectly balanced seesaw or a picture hanging straight on a wall. Those are examples of rotational equilibrium.
That makes sense.
Yeah.
So we've talked about the force that starts the spin and the balance that keeps things steady. What happens when objects are moving A and D rotating at the same time?
That's where we get into plane motion.
Okay.
Think about a ball rolling down a hill. It's not just rotating, it's also moving forward in a straight line. To analyze this kind of motion, we need to consider both the forces acting on the object's center of mass and the torques causing it to rotate.
Okay. I think I'm starting to see how this all fits together, but I'm guessing this is just the tip of the iceberg when it comes to rotational dynamics, right?
You're absolutely right. There's so much more to explore, from the energy of rotating objects to the fascinating concept of angular momentum.
Okay.
But I think we've laid a solid foundation for our deep dive.
I'm ready to keep spinning. Where do we go from here?
Welcome back. Are you ready to delve deeper into the world of spins and turns?
Absolutely. I'm all warmed up and ready to tackle some more of those physics brain twisters.
Great. Let's start by zooming in on a specific type of rotation called pure centroidal rotation.
Centroidal rotation. That sounds fancy. Break it down for me.
It's simpler than it sounds.
Mm-hmm.
Imagine a spinning top, perfectly balanced on its tip, or a basketball spinning smoothly on your finger.
Okay.
That's centroidal rotation, where the object spins around a fixed axis that passes right through its center of mass.
So because the axis goes through the center, it just spins cleanly without wobbling or moving around.
Precisely. And because the center of mass isn't moving, we only need to worry about the rotational forces or torques acting on the object.
Okay, that makes sense.
Mm.
But what happens when things aren't so perfectly balanced? What if the axis of rotation is off-center?
That's when we move from pure centroidal rotation to a scenario where the axis is fixed but doesn't pass through the center of mass.
So now we're talking about things that not only rotate but also move in a circular path?
Exactly. Think of a door swinging open on its hinges. The hinges are the axis of rotation, but the door's center of mass is off to the side.
Right.
So as the door rotates, it also sweeps out a circular arc.
So now I've got to consider both the linear forces and the rotational forces,
Yeah.
right? It's getting a bit more complex.
It does add a layer of complexity, but the principles we've already discussed still apply. We just need to use both the force equations, which govern the linear motion of the center of mass, and the torque equations, which govern the rotation around the axis.
Okay, so it's like we're juggling two sets of equations now. One for the straight line movement and one for the spinning.
That's a good way to visualize it. Now let's broaden our perspective even further and talk about general plane motion.
General plane motion, is that where things get really wild?
Not necessarily. General plane motion simply describes any motion that combines both translation and rotation, regardless of where the axis of rotation is.
So it's like an umbrella term that covers all sorts of complex movements, right?
You got it.
Oh.
A ball rolling down a hill, a wheel turning on a car, a gymnast flipping through the air. These are all examples of general plane motion.
Okay, so how do we even begin to analyze something that complex?
There are a couple of approaches. We can either think of it as the center of mass moving in a straight line, while the object simultaneously rotates around that center.
Okay.
Or we can imagine an instantaneous axis of rotation.
Wait, an instantaneous axis, what does that even mean?
It's a pretty cool concept. Imagine a line passing through the object at any given moment that represents the axis around which it's rotating at that precise instant.
So it's not a fixed axis like the hinges of a door.
Right.
It's a constantly shifting axis depending on how the object is moving.
Exactly. It's a mathematical tool that helps us break down complex motions into simpler components. For example, with our ball rolling down a hill, the instantaneous axis of rotation would be the point where the ball touches the ground at any given moment.
I'm starting to wrap my head around that. But what about momentum and energy in all these complex rotational scenarios?
Yeah.
Do those concepts still apply?
Absolutely. Remember angular momentum. It's a measure of an object's tendency to keep rotating. And just like linear momentum, angular momentum is conserved.
Okay.
It can be transferred between objects or between the rotational and translational motion of a single object.
Sure.
But the total amount within a closed system always stays the same.
So it's like energy, it can change forms, but it never disappears completely.
Yeah.
I'm sensing a pattern here.
You're picking up on some fundamental principles of physics. These conservation laws are incredibly powerful tools for understanding how the universe works.
This deep dive is seriously expanding my understanding of the universe. Now, I'm curious about rolling motion. We encounter rolling objects all the time, from car tires to bowling balls.
Yeah.
What makes rolling unique from other types of motion?
Rolling is a fascinating blend of translation and rotation, where the point of contact between the rolling object and the surface is momentarily at rest.
Okay.
This no-slip condition is key to understanding how rolling works.
Hold on, you're saying the point on the object that's touching the ground is actually stationary for a split second.
Precisely. It's like the object is pivoting around that point of contact as it rolls. And because of this no-slip condition, the linear speed of the object's center of mass is directly related to its angular velocity.
So if a wheel is rolling faster, it's also spinning faster.
You got it. Now, we can further break down rolling into two categories. Rolling without slipping, which we call pure rolling, and rolling with slipping.
Okay, what's the difference?
In pure rolling, there's no sliding or skidding. The point of contact is truly instantaneously at rest. But in rolling with slipping, there's some relative motion between the object and the surface at that point of contact.
So a car tire spinning on ice would be rolling with slipping, while a tire rolling smoothly on dry pavement would be pure rolling.
Perfect examples. The amount of friction between the object and the surface plays a big role in determining whether it's pure rolling or rolling with slipping.
That makes sense. Now, how does kinetic energy fit into all of this? Is the energy of a rolling object simply the sum of its translational and rotational kinetic energies?
You're on the right track. We do need to consider both translational and rotational kinetic energy. But here's the cool part. In pure rolling, the ratio between these two forms of energy is fixed for any given object.
Oh.
It depends solely on the object's shape, or more specifically, how its mass is distributed.
So a solid cylinder rolling without slipping will have a different split between translational and rotational energy compared to a hollow cylinder of the same mass and radius.
Exactly. The distribution of mass within the object dictates how its kinetic energy is divided between its movement through space and its spinning motion.
I am amazed by how much complexity there is in something as seemingly simple as rolling.
It's true, rotational dynamics can be surprisingly intricate. But the more we understand these concepts, the more we appreciate the elegant way the universe works.
I'm feeling pretty energized after all this spinning and rolling. What other rotational wonders await us in this deep dive? Welcome back. I'm ready for the grand finale of our rotational dynamics deep dive. What other mind-bending concepts do you have in store for me?
Well, we've covered a lot of ground, but there's one more fascinating phenomenon we need to explore. Eccentric impact.
Eccentric impact. That sounds intriguing. What is it?
It's what happens when objects collide off-center.
Okay.
And it's way more interesting than a simple head-on collision. Think of billiard balls. A direct hit will transfer linear momentum, sending the balls moving in predictable directions. But a glancing blow introduces angular momentum, causing the balls to spin in addition to moving.
So the angle of impact is a big factor in determining how the object behaves after the collision.
Absolutely. And it's not just the angle. The masses of the objects, their shapes, even the materials they're made of, all come into play.
It's amazing how much complexity is hidden in something as seemingly simple as two objects bumping into each other.
It's true. And understanding eccentric impact is crucial in so many fields.
I bet.
From designing safer cars to predicting the paths of asteroids in space.
Now, you've mentioned angular momentum quite a bit, but
Right.
how do we actually measure this tendency of objects to keep spinning?
That's a great question. The angular momentum of a single particle is defined as the cross product of its position vector and its linear momentum.
Okay.
For a rigid body, which is made up of countless particles, we integrate over all these particles to get the total angular momentum.
Okay, I'll admit that's a bit over my head. Can you give me a more intuitive sense of what angular momentum represents?
Of course. Picture that figure skater again, spinning with their arms outstretched.
Yeah.
Their angular momentum is a measure of how much they want to keep spinning in that state. When they pull their arms in, their moment of inertia decreases, remember?
Right.
But their angular momentum has to remain constant, so their angular velocity increases, making them spin faster.
That's why they spin faster when they tuck in their arms.
Yeah.
It all comes back to that conservation principle.
Exactly. Conservation of angular momentum is one of the most fundamental laws of physics, and it explains a wide range of phenomena, from the stability of gyroscopes to the way planets orbit stars.
This deep dive has been a whirlwind of information. I feel like I've gone from 0 to 60 in rotational dynamics. Any parting thoughts before we wrap things up?
Just this. Rotational dynamics is all around us. From the spinning of electrons and atoms to the rotation of galaxies, it's a fundamental part of how the universe works.
I never thought about it like that.
So keep asking questions, keep exploring, and never stop being curious about the world.
And on that note, We've reached the end of our rotational dynamics journey. We've spun through concepts from rigid bodies to eccentric impacts, and I hope you're leaving with a newfound appreciation for the forces that make the world go round. But here's one last thought to ponder. What would happen if Earth suddenly stopped spinning? Until next time, keep those wheels turning.